Welcome students once again into the class of number theory, and we are doing in these videos nowadays concept of congruences. As promised in the previous video, I'll deal with some questions related to congruences and not with the heavy theorems. So some easy basic fundamental questions related to the concept of congruences. So let us start with one simple question, and the first question what I'm going to take today is write down the statement of the theorem and then we will move on to the proof. For every prime number p greater than 5, either p square minus 1 or p square plus 1 is divisible by 10. This we have to prove. So what is given to us is that p is a prime number and is greater than 5. Now proof, or you can say solution of this question is very easy. Since p is greater than 5 and is prime, p is prime and is greater than 5, one thing is clear, that p is odd, because the only prime number which is even is 2 and it is less than 5. Our prime number is greater than 5, so it must be odd. And if p is odd, p square must also be odd, because square of an odd number is odd always. And if p square is odd, then p square minus 1 and p square plus 1 are both even. That means 2 divides p square minus 1 and 2 divides p square plus 1. Now if we prove that either 5 divides this or 5 divides this, so if 5 divides p square minus 1, then 2 divides p square minus 1, 5 divides p square minus 1, and GCD of 2 and 5 is 1. Therefore 2 into 5, that means 10 will divide p square minus 1. Similarly, if 5 divides p square plus 1, then 2 also divides p square plus 1, and GCD of 2 and 5 is 1. So 2 into 5, that means 10 will divide p square plus 1. That means the only thing remain to prove now is to prove that 5 divides either p square minus 1 or p square plus 1. Now p is odd. I am going back. P is odd. So what about p square now? P is odd. What about p square? If p is odd, its last digit is 1, 3, 5, 7 or 9. One of these digits will be in the last place. Secondly, 5 cannot be, because if the 5 is the last digit, the number will not be prime. It will always be divisible by 5. So we omit, we delete that part, particular 5. Now what about p square? If p is having last digit 1, then the last digit of p square is also 1. So that means your p square is congruent to 1. Is congruent to 1 modulo 10. Because we are talking about the last digit. If it is 3, if the last digit of p is 3, then what will be the last digit of p square? Definitely it will be 9. So your p square will be congruent to 9 modulo 10, because when you are taking modulo 10, that means you are dividing this number p square by 10 and you are only considering the remainder. And remainder means the unit digit, because if a number, suppose you are taking this number 2, 5, 1, 3, 6, 2 and you divide it by 10, then what the remainder you will get will be the last digit of this number. So whenever you are taking some number and you are making it congruent modulo 10, then what the result you are obtaining is actually the last digit. So I think in this way I don't need to prove that 5 divides p square minus 1 or 5 divides p square plus 1. Directly we will get that 10 divides p square minus 1 or 10 divides p square plus 1. Once again, this is p square congruent to 9. Modulo 10. I am writing modulo 10 after some space because now I am going to write this 9 as 10 minus 1. And if you are having a congruence equation, suppose you are having A is congruent, A plus B plus C is congruent to D plus E plus F plus G modulo M, then if some numbers from these A, B, C, D, E, F or G, if they are multiple of M, you can leave them. Suppose your M divides C. Suppose your M divides C, then by deleting C from here, the congruence equation will be still okay, will be still right. Suppose your E is also a multiple of M. Maybe your C is equal to 7M, maybe your E is equal to 17M, so you can delete E also. If your F is say 1 million M, 10 million M, 1000 M, 991 M, that is a multiple of M, so you can delete F also, and your congruence equation will still be okay, will still be right. So here the same concept I am going to use, that this p square is congruent to, leave this 9 now because instead of 9 I have written now 10 minus 1. And in this congruence equation you are taking modulo 10. And can you find any number here which is a multiple of 10? Yes. Here you are having 10. It is a multiple of 10. So you can leave it. And your congruence equation is still okay. That means your p square is congruent to minus 1 modulo 10. This is the case when your last digit is 3 for p. Now what will happen if it is 7? Once again, if your number is having 7 in the units place, squaring 7 7s are 49, so what will be the unit digit? Is once again 9. So once again you will get 9 here modulo 10. But now you know that this 9 can be written as 10 minus 1, and 10 being a multiple of 10 can be removed. So once again your p square is congruent to minus 1 modulo 10. So third case is okay. Now fourth, your p is congruent to 9 modulo 10. So what will happen to p square? 9 9s are 81. So what is the units digit is 1. So your p square is congruent to 1 modulo 10. From the first one, you can see that p square is congruent to 1 modulo 10 means 10 divides p square plus 1. So 10 divides p square plus 1 if your p is having 1 or 9 in the units place. In both these cases, p square minus 1 will be divisible by 10. And what is for the remaining two cases? Remaining two cases means if your units digit is 3 or 7, then p square is congruent to minus 1 modulo 10, and using the definition of congruences, 10 will divide p square minus 1, that means 10 divide p square plus 1. Sorry, in the first case I have written p square plus 1, it should be p square minus 1. Because if a is congruent to b modulo m, m divides a minus b, not a plus b. I have written a plus b, sorry, it is a minus b. So if the first or last case is there, your 10 will divide p square minus 1, and in the second or third case your 10 will divide p square plus 1. And these are all possibilities. There is no more possibilities. That means 10 will always divide either p square minus 1 or p square plus 1 if p is a prime number greater than 5. So next I am moving to another question of the same type. The questions are all very easy, very interesting, as the concept of congruences is an easy and interesting concept. So second question what I am going to take is, some people are having doubt that if a square is congruent to b square modulo m, then a is congruent to b modulo m, or A is congruent to minus B modulo M. Some people have this confusion in their mind, but it is not true. A square is congruent to B square does not imply A is congruent to B modulo M or A is congruent to minus B modulo M. Maybe this is true and these both are not true. So what we have to do to prove this, we will have to give some counterexample, and counterexample is once again very easy. You just take your A as 3, your B as 0 and your M as 9. Look at this equation first. Is it holding? Is it true? Yes, it is, because A square is 9, congruent to B square is 0 and modulo your M is 9. And it is true because this 9 divides 9 minus 0. That means 9 divides 9. It's okay. But what about these two? What about these two? Is any of these two is true? No. Neither this is true nor this is true. Because 3 congruent to 0 modulo 9 is not true. It gives 9 divides 3, which is not the case. And if you will consider the second case, once again, you will get 3 congruent to 0 modulo M. That means, 9. That means once again you are getting 9 divides 3, which is not true. 3 divides 9, but 9 does not divide 3. So, if A square is congruent to B square modulo M, it does never mean either A is congruent to B modulo M or A is congruent to minus B modulo M. This is not true. This is not the case. So, this was a counterexample to show that here A square congruent to B modulo M does not imply A is congruent to M or congruent to B modulo M or A is congruent to minus B modulo M. Moving on to the next question. Very easy once again. N is odd if and only if N is congruent to 1 modulo 2. It's a very easy example, very easy question. Just you can visualize it in your mind. If and only if, so we'll have to give both way proof. The direct proof as well as the converse, and both are just 2 or 3 liner proofs. So suppose N is odd. If your N is odd and you divide your N by 2, what the remainder you are going to get is 1. And whatever the quotient is there, let it be Q. If you divide N by 2, your remainder is 1, and whatever the quotient Q is there, you can just put here Q. And from this, you can write N is equal to 2 times Q plus 1. Your N is equal to 2 times Q plus 1. Is it true? So this is your N. Take this 1 to the side. So N minus 1 is equal to 2Q. Now, right hand side is 2Q, is a multiple of 2. So it is divisible by 2. If right hand side is divisible by 2, left hand side must also be, because they are equal. So that means your 2 divides N minus 1. And M divides A minus B means A is congruent to B modulo M. So M here is 2. So N is congruent to 1 modulo 2 is there. So direct proof is very easy. Converse is also very easy. Because now conversely, suppose you are given that N is congruent to 1 modulo 2. By using the definition of congruences, you can have 2 divides N minus 1. And if 2 divides N minus 1, that means your N minus 1 is a multiple of 2. Now take this one to the other side. N is equal to 2m plus 1. And you know very well that every number of the type 2m plus 1, 2 times something is even and plus 1 is odd. So this means your N is odd. So both way we have proved this theorem, which was just 2 or 3 liner. Very easy proof. You can just keep it in mind. You can calculate, you can visualize this result in your mind as well. Another question I'm taking once again, very easy question. Fx is a polynomial with integral coefficients and f of a is congruent to some integer k modulo m, you write if here. If fx is a polynomial with integral coefficients and fa is congruent to k modulo m, then f of a plus mn is also congruent to k modulo m for every integer n. For every integer n. So this is another result we are going to prove. Let us have a look at the solution. What the solution says. What we are given, fx is a polynomial with integral coefficients. So and secondly we know that fa is congruent to k. We are given that fa is congruent to k modulo m. This is given. Note that your a plus mn is congruent to a modulo m. Why? Because your m divides a plus mn minus a. A is cancelled out, m divides mn is very much obvious. So this result is true. In the previous video, we worked on one result, that is if a is congruent to b modulo m and f is a polynomial with integral coefficients, then f of a is congruent to f of b modulo m. This result we have proved in previous video, and this result I am going to use here now. In place of a and b, I am having here a plus mn and a. This is a plus mn congruent to a modulo m, and your f is a polynomial with integral coefficients. That means f of a plus mn is congruent to f of a modulo m. Now once again see that your f of a plus mn is congruent to f of a modulo m, but this f of a is congruent to k modulo m, and we know that the relation of congruences is a transitive relation. If a is congruent to b and b is congruent to c, then a is also congruent to c directly. So using the transitivity of congruences relation, you can directly write now f of a plus mn is congruent to fa, and fa is congruent to k, so this is congruent to k modulo m, and it is true for every n belonging to the set of integers. So this was an easy result. However, the result was looking a little bit difficult, but it is not difficult. The proof is very easy. So with this question we are moving on to the next question based on easy fundamental properties of congruences. So what the next question is? Next question, write down if n is a composite number, if n is a composite number, then n minus 1 factorial is congruent to 0 modulo n except for n is equal to 4. The result is not true if n is equal to 4, otherwise result is always true. So let us see what the solution says. Let n be a composite number. Let n be a composite number. If n is a composite number, then definitely it will have some factorization other than 1 and n. So let the factorization be n is equal to ab, where 1 is less than a is less than or equal to b is less than n. We can always have this type of factorization if n is a composite number. Now here there may be 3 cases. In case n is equal to 4, what these two factors are? These are 2 and 2. That is the only possibility. For n is equal to 2, for n is equal to 4, we have to show that this result is not true. because we have to prove this result except for n is equal to 4. That means for n is equal to 4 the result does not hold. If n is equal to 4, what the factors are? 2 and 2. There are distinct factors, but what about this result? This result will become 3 factorial is congruent to 0 modulo 4. And what is your 3 factorial is 6. 6 congruent to 0 modulo 4 means 4 divides 6 is a contradiction, because 4 does not divide 6. So this we have proved that for n is equal to 4 this result will not hold. Otherwise it will always hold. So let us see what will happen if n is not equal to 4. If n is not equal to 4, once again from here you can have two possibilities. One possibility is your A is equal to B. One possibility is that your A is equal to B. And if A is equal to B, then what your number n will be? N will be A into A, that means A square. And A square is greater than 2A for every composite number n which is not 4, greater than 4. Your A square is greater than 2A. That means your n is greater than 2A. And if n is greater than 2A, n minus 1 can be at the most greater than or equal to 2A. N is strictly greater than 2A, but n minus 1 can be greater than 2A or maybe equal to 2A at the most. If n minus 1 is greater than or equal to 2A, it means when you will write n minus 1 factorial, when you will write n minus 1 factorial, in the product you will have A as well as 2A. So A will divide this number, 2A will also divide this number. A will divide this number, 2A will also divide this number. So n minus 1 factorial is divisible by A and by 2A. So it is divisible by A into 2A also. It is having A as a factor. It is having 2A also as a factor. So that means A and 2A, their product will also divide n minus 1 factorial. So what is A into 2A? Is 2A square. So that means, and what is your A square? Your A square is n. So this is 2n, you can say now. So n minus 1 factorial is divisible by 2n. So that means 2n divides n minus 1 factorial. 2n divides n minus 1 factorial. And n divides 2n without any doubt. Without any doubt, n divides 2n. 2n divides n minus 1 factorial, and divisibility is a transitive relation. A divides B, B divides C, that means A divides C. So you can directly say that n divides n minus 1 factorial. So I am writing here n divides n minus 1 factorial, and you can write here minus 0. M divides A minus B. M divides A minus B means A is congruent to B modulo M. So from here you can directly write n minus 1 factorial is congruent to 0 modulo n, and we have proved the required result. But it is the case when A is equal to B. If A is not equal to B, what will happen then? So the other case when A is not equal to B. A is not equal to B means 1 is less than A is less than B is less than, and this is the case now. Once again, A is less than B n, B is less than n. B can be at the most equal to n minus 1, because B is strictly less than n, it can be at the most equal to n minus 1. So once again, your n minus 1 factorial will have a factor A as well as a factor B. So you can say n minus 1 factorial is divisible by A and is divisible by B. If n minus 1 factorial is divisible by A as well as by B, you can say your n minus 1 factorial is divisible by their product A into B, but A into B is now your n square, n. So this means your n divides n minus 1 factorial, and once again you can write here minus 0. And m divides A minus B by the definition of congruences, you can directly write your n minus 1 factorial is congruent to 0 modulo n. So this was another important result to be proved today, and now we are moving on to very interesting 3 results which you will use again and again while you are doing your number theory, your questions related to number theory. These 3 results will be always useful. So what these results are: number 1 is that a square is congruent to 0, 1, 4, 5, 6 or 9 modulo 10. When you are doing modulo 10, that means directly you are talking about the units digit. That the units digit of any number, any natural number a, it can be 0, it can be 1, it can be 4, it can be 5, it can be 6, it can be 9, but it can never be 2, 3, 7 or 8. That's what we wanted to prove here. So, if a is congruent to 0, a is congruent to 1, a is congruent to 2, a is congruent to 3, a is congruent to 4, a is congruent to 5, a is congruent to 6, a is congruent to 7, a is congruent to 8, a is congruent to 9. These are the all possibilities, modulo 10. Modulo 10, these are the all possibilities. If you will divide a number by 10, then your remainder can be 0, can be 1, can be 2, can be 3, can be 4, can be 5, can be 6, can be 7, can be 8 or can be 9. These are the only possibilities. There is no more possibility. All the possibilities I have written down here on the board. Now square. Squaring, what you will get? In the first case, a square is congruent to 0 square, because we know that if a is congruent to b modulo m, then a square is also congruent to b square modulo m. So a square is congruent to b square modulo m, and 0 square is 0, so no need to change it. Your a square when divided by 10 will give you remainder 0. That means 0 can be the last digit. In the second case, the same thing. A square is congruent to 1 square and 1 square is 1. So a square can be congruent to 1 modulo 10. Third case, a square is congruent to 2 square, and what is 2 square is 4. So a square can be congruent to 4 modulo 10. If a is 3, a square will be congruent to 3 square, and 3 square is 9. So a square is congruent to 9 modulo 10. If a is congruent to 4, squaring both sides, your a square is congruent to 16. But 16 can be written as 10 plus 6. And I have told you if in a congruence equation you are having a number which is divisible by the modulo number m, then it can be removed. So here 10 is a multiple of 10, so this 10 can be removed. You will be left with a square is congruent to 6 modulo 10 in this case. If a is congruent to 5, your a square is congruent to 5 square, and 5 square means 25, and 25 can be written as 20 plus 5, and once again your 20 is a multiple of 10, so it can be removed, and a square will be congruent to 5 modulo 10. This will be the least positive remainder when a square is divided by 10. In the next case, a square is congruent to 6 square, and 6 square means 36. Once again, this 36 you can write it as 30 plus 6, and this 30 being a multiple of 10 can be removed. So a square is congruent to 6 mod 10. If a is congruent to 7, a square is congruent to 7 square, and 7 square means 49, and 49 you can write it as 40 plus 9, and once again 40 being the multiple of 10 can be removed, so you are left with a square is congruent to 9 modulo 10. If a is congruent to 8, then a square is congruent to 8 square. 8 square is 64, and 64 once again can be written like 60 plus 4, and 60 being a multiple of 10 can be removed, so you will be left with a square is congruent to 4 modulo 10. In the last case, a square is congruent to 9 square. 9 square is 81. 81 once again can be written as 80 plus 1, and 80 being a multiple of 10 can be removed, so you will be left with a square is congruent to 1 modulo 10. So your a square modulo 10 is congruent to 0, 1, 4, 4. There are two cases, 0, 1, 4 in two cases, 9 once again in two cases, then 6 again in two cases, 5. So 1 again in two cases. So all the possibilities are covered. So if you take any natural number and if you want to find what number it is congruent to modulo 10, then these are the only possibilities: 0, 1, 4, 5, 6 and 9. A square is never congruent to 2, 3, 7 or 8 modulo 10. That means in units place of square of any natural number, you can never find 2, 3, 7 or 8. So this was this result, this question. And from here directly we can move on to another result. Now you know that your a square can be congruent to 0, a square can be congruent to 1, a square can be congruent to 4, a square can be congruent to 5, a square can be congruent to 6, a square can be congruent to 9 modulo 10. That means if you divide a number by 10, square of a number by 10, your units place is either 0, 1, 4, 5, 6 or 9. What about a raised to the power 4? So square once again. Squaring once again, here in the first case you will get a power 4 is congruent to 0 square, and 0 square means 0. So a power 4 modulo 10 is congruent to 0. That means power 4 of a number when divided by 10 can leave remainder 0. Okay. Second case is again similar. A power 4 is congruent to 1 square. Once again 1 square is 1. No problem, it's okay. In the third case, it is a power 4. Here you will get 4 square, and 4 square is 16, and 16 you can once again write it like 10 plus 6, and 10 being a multiple of 10 can be removed. So a power 4 can be congruent to 6 modulo 10. It cannot be congruent to 4 now. Another possibility is being deleted. A square is congruent to 5, so a power 4 is congruent to 5 square, and 5 square is 25. 25 once again you can write as 20 plus 5. So 20 being a multiple of 10 can be removed. So a power 4 is congruent to 5 modulo 10 is possible. Next case, once again a power 4, 6 square. 6 square can be written as 36. 36 can be written as 30 plus 6. And since you are having modulo 10, multiple of 10, that means 30 can be removed. So a power 4 can be congruent to 6 modulo 10. And in the last case, a power 4, 9 square. 9 square is 81. 81 once again can be written as 80 plus 1, and 80 being a multiple of 10 can be removed. So a power 4 is congruent to 1 modulo 10. That means a power 4 can be congruent to 0, 1, 5 and 6 modulo 10. So there are now, earlier there were 6 possibilities. That means square of a number can have 0, 1, 4, 5, 6 or 9 in the units place, whereas power 4 of a natural number can have only 0, 1, 5 or 6 in the units place. In the units place of a raised to the power 4, for any natural number a, you can never have 2, 3, 4, 7, 8 or 9. You always will have in the power 4 of a natural number at units place either 0 or 1 or 5 or 6. So this is another important result regarding number theory, which will be used later on when we will do Fourier fractions, continued fractions and so on. But here it is an important result, and the last result what I am going to prove is that a cube is congruent to 0, 1 or 8 modulo 9. I am not taking the case modulo 10 now. This is a question. This is a question to be proved, that you can write here, prove that a cube is either congruent to 0 or 1 or 8 modulo 9. Now look at whatever the number a is, whatever natural number a is, if you divide a by 3, there may be any question, but there are only 3 possibilities for the remainder. It can either be 0 or 1 or 2. There is no fourth possibility. You cannot have here 3, because if 3 is the remainder, more division is possible. You will get remainder 0. If you are having 5 here, more division is possible. You can have remainder 2. So your a number, every natural number can be written like either 3q plus 0, or 3q plus 1, or 3q plus 2. So every natural number can be written like either 3q or 3q plus 1 or 3q plus 2, and we will consider all these 3 cases. If your a is of the type 3q, what will happen? If your a is 3q, what is your a cube? It is 27q cube. And if you take modulo 9, if two numbers are equal, if a is equal to b, then always a is congruent to b modulo any number. You can take any m here. Here these two are same, so you can take them congruent to each other modulo anything. So I am taking 9 here. What is required to me in this question for the solution? So I am taking modulo 9. And you know, in a congruence relation, if there is something which is multiple of the modulo number, then it can be removed. I am writing here 27q cube plus 0. I think you will have no problem. And 27q cube is a multiple of 9. And if in a congruence equation a number is a multiple of modulo number, then it can be removed. So you will have no objection if I will remove 27 cube here. So what you will get? You will get a cube is congruent to 0 modulo 9. So in case your a is of the type 3q, your a cube will be congruent to 0 modulo 9. Now look at the second case. If your a is of the type 3q plus 1, once again cubing both sides, you will get a cube is equal to 27q cube plus 27q square plus 9q plus 1. Now these two numbers are equal, and I have told you that if a is equal to b, then you can write a is congruent to b modulo m for any m. And now these two numbers are same, so I can write they are congruent to each other modulo any number, and any number I am taking here as 9. Once again the same theory. This is a congruence equation, modulo 9. So any multiple of 9 can be removed. This is a multiple of 9, can be removed. 27q square is a multiple of 9, can be removed. 9q is a multiple of 9, can be removed. So what you are left with is a cube is congruent to 1 modulo 9. So in the second case, when your number a is of the type 3q plus 2, a cube is congruent to 1 modulo 9. And the third case, when your a is of the type 3q plus 2, on the same lines, you can prove that a cube is congruent to 8 modulo 9. So this part I am going to leave you as an exercise. Do it, complete it, and here I am going to stop this video. In the next video we will have more and more theorems, properties, questions on congruences. Till then, thank you once again.